Welcome to the Future of Structures podcast, where we talk to the experts who are evolving our buildings for tomorrow. And here is your host, Adam Jones.
Today we are speaking with Danielle Tensley Tingley, who is a Professor of Architectural Engineering at the University of Sheffield. Her research focuses on how to reduce the embodied carbon of our buildings. So you might have heard on this show before that cement alone accounts for 8% of the whole world's greenhouse gas emissions, which is actually more than cars on our roads. So if we are to move to a low carbon economy, we inevitably won't be able to stop just at operational energy. We will also need to find the methods to reduce embodied energy down to zero also. So in this episode we discuss the circular economy of construction materials, the feasibility of designing for deconstruction, reuse of existing buildings and downcycling of construction materials, and how to improve the efficiency of material use in structural design. So Danielle is an expert in an increasingly important field. It was a pleasure speaking to her. I hope you guys learned as much as I did speaking to her. And without any further ado, here is Danielle.
As an undergraduate at Sheffield University, studying structural engineering and architecture, it's kind of a bit of a hybrid of career paths, and then went straight from that into PhD, looking at design for deconstruction and material reuse, and the embodied carbon benefits, so benefits associated with materials from that kind of strategy, particularly looking at structures. And then I did a couple of different postdoc research positions, one at Sheffield, then one at the University of Cambridge, then back to Sheffield, then got my lectureship at Sheffield about 2 years ago now.
Awesome. So were you from the very start of your career interested in sustainability, and is that what drove you to be where you are today?
That's a great question. So I guess when I came in as an undergrad, I was probably more interested in kind of how do I use maths in a useful way. And then as I went through, I was questioning how do I kind of do something useful with my degree, and is engineering the right place to do that, and very nearly switched courses and went into medicine. But actually decided, you know what, when you look at the material impacts of engineering, it has such a big impact on the planet that actually trying to look at different ways of reducing those material impacts and designing in different ways could actually be a really good way to make a kind of difference, I guess. Not initially, but probably towards the end of my undergrad degree, and then very much with my PhD choice,
For a lot of people, it's not a very, I guess, sexy topic, embodied energy and solutions in that area compared to operational energy. Do you see this kind of trend and focus toward embodied energy potentially increasing in the future?
Yeah, absolutely. So it's barely been on the radar probably since I started working in it, back in 2009 now, it's nearly 10 years ago. And I'd say in the last 5 years probably in the UK, it's become much more talked about than it was. And as we decarbonise the electricity grids, our operational energy is kind of inherently going to start to go down. And I think we know what to do a lot better with operational energy in terms of building design. Yeah. Actually, it's not, the challenge is implementing it. It's not what are the technical solutions. Whereas with embodied carbon and energy, actually the technical solutions really aren't there yet. Design strategies aren't there. And I think it's kind of going to be the biggest challenge the building sector has to face in the next couple of decades, because we don't really know fundamentally what to do with some of it.
Yeah, that's right. And I read a stat, and there's different stats in wherever you look, but one anyway said that cement is 8% of the whole world's emissions, and that's actually more than the cars on our roads. And then obviously you got the rebar, what's not included in that, and then you got steel, and all up the embodied energy of our structural products do add up to quite a bit. And in the next 40 or so years, we have to get these to zero emissions. So then the technical solutions have to come from somewhere. So I guess that's what we're going to be talking about today, what these technical solutions might be.
Absolutely. And there's some stats from the University of Leeds, who I work with quite often, and they've looked at the proportion of embodied energy to operational energy, or carbon, in the UK construction sector. And from 2010 to 2014, it went from 18% to 26% in terms of kind of relative emissions.
Wow.
So we're already seeing this huge shift that actually embodied carbon is a quarter of UK construction emissions.
Yep.
And that is just going to keep increasing as a proportion.
Yeah, awesome. So you mentioned earlier some of your research is in this space, and one of those you mentioned is designing for deconstruction. Can you tell us a little bit about that and what it might look like and the feasibility of this?
Yeah, sure. So design for deconstruction at a very fundamental level is trying to design so that you can take a building apart fairly systematically and then reuse the different components. So if you think kind of Lego, Meccano that you played with as a kid, that's sort of what you're aiming to do with whole buildings, with structures. The feasibility, I think, we're already starting to see kind of trial versions and structures that are designed in this way, particularly in a lot of temporary buildings or short lifespan buildings, where, you know, if they've got a use for 5 years, absolutely you need to be able to take that thing down and reuse those components. So I think the technology is there. It does change and give you certain challenges around floor slabs particularly, and how you're connecting floor slabs into your structure. And certain materials absolutely lend themselves better than others. So steel and timber, in terms of structural materials, are going to be much easier materials to design with in this way because you can have reversible connections. Whereas things like reinforced concrete is going to present a whole load of challenges because in situ, you're clearly the way you construct it, you're never going to get that apart. Are a couple of examples with precast where they've tried to deconstruct it.
Yep. How'd they go?
A lot of damage. So they did manage to reuse parts. This was in the Netherlands. So they took it apart and then reassembled a bit. But yeah, the damage rate was just really high because concrete is not really designed to be taken apart.
Yeah. So was that precast walls and precast elements of the floors as well? Is that what they tried to do?
Yep. Yeah. I can't remember what the exact damage rate was, but it was pretty high.
Yep.
Whereas you just wouldn't be getting that damage rate with other materials.
Yep. So on the flip side, say with steel and timber, with steel, what kind of design strategies do you need to employ to make sure you can actually, deconstruct the building at the end of life?
So it's predominantly kind of reversible, accessible connections. So bolted connections is or pinned connections is the ideal. Some demolition contractors will tell you they're going to cut it out anyway, so that doesn't make a huge amount of difference. I guess it depends who's deconstructing end of life and if they've got that kind of vision of how you were going to deconstruct this building in the first place. And then with steel, the floor slab becomes kind of your big challenge, really. So you avoid composite floor slabs where you've got composite decks, where you've got shear studs that are connecting through to the beams every kind of 400 to 600 mil. You're much better with kind of a precast concrete unit or a CLT floor that has much fewer connections. But that with steel, those are kind of the key. And then a deconstruction plan, really. And ideally, some marking on the material or kind of material passport ideas that give you additional information about, say, what steel grade you're designing with, so that in the future, I've got S275 steel. I know I know what assumptions to make here. Exactly.
So that sounds like it's half the equation, or half the battle is designing for deconstruction. By the end of life, I mean, is it what will make us want to reuse the steel beams? How can we cross that hurdle? Because it seems like you need the economies of scale there at the very start, or big stockpiles of steel beams to choose ones that are kind of fit for purpose.
Yeah, so that's a huge challenge, I think. There's a project I worked on when I was at the University of Cambridge where we started to look at this with some of the kind of client sector and construction sector generally. And there's this kind of chicken and egg situation of, well, you almost want people to be demanding reuse steel, so that the demolition sector can kind of respond and say, oh, okay, there's actually an economic benefit for us doing this. Let's absolutely respond, and then you build up that stockpile. Equally, if the stockpile's there, it's much easier for people to reuse, so you end up with this really difficult relationship. And there are some kind of material exchange websites and that kind of thing that are starting to be tested to say, okay, can you start to match this so that, as you're about to demolish a building or considering demolishing a building, you can flag what materials are going to become available, and then let someone say, oh, yeah, those are absolutely what I need for my construction project. I'll have those. At the moment, I think you see a lot more of reusing materials that are already on the site, where you've got an existing building on site, inherently because you know those materials are there, you know you can access them. You may well have the demolition contractor linking through to the contractor that's doing the main build. So I think that makes it easier. But in the long term, I think it's absolutely going to be that demolition contractors or others need to see that there's a business case and that there's a monetary benefit. And there is, they salvage architectural type features because they know there's enough of a market in the UK that it's worth doing that. And a reused brick, for example, can be worth more than a new brick, which is kind of insane. But actually there's the kind of architectural aesthetics that come along with a brick, which I don't think you're going to get with structural materials in the same way. But the associated embodied kind of benefits of that, and particularly if we started to shift to something like a carbon tax, where materials were inherently getting more expensive because of their carbon intensity. If you've got reused elements, you could see them getting that kind of discount for that and actually driving the economic reasons as a designer that you want to try and use those materials, and then increasing that demand, which hopefully means that the market will react. Yeah,
it sounds like if we brought in that carbon tax, the case for all of this, changes quite dramatically and quite quickly, and all of a sudden that you are incentivizing all these solutions we're talking about now. It also sounds like things like building information modeling. If you got a really good model, when you demolish, or the decision to demolish at the end of life, you've got all this additional information to know exactly, how much value is contained in the building, and help the decisions, I guess, in that stage.
Yeah, I definitely think so. And in the UK, kind of material passports an idea in the last couple of years have been talked about way more as, you need to know what that material is that needs to go with this material or building through life, so that you have this kind of inventory of a building that a demolition contractor can look at in 20, 30 years. For some buildings, some buildings in London really don't have a long lifespan. Ideally, we're looking at 60, 80 years or 100 years, but you've got that then that people in the future can say, okay, I know exactly what I should be able to get out of this, what the value therefore is of this. And you just make life much, much easier rather than having to do demolition audits and bring in professionals to kind of have a look and assess those benefits.
I guess another solution that people can do, and this, I think you've done some work in this area as well, is actually reusing the existing building rather than demolishing it in the first place. So from the high level, what's the case for reusing existing buildings?
Yeah, so I suppose in terms of kind of your hierarchy of waste and a hierarchy of reuse, reusing your building is kind of the first thing you'd go to, because that's where you've got almost the maximum amount of value and maximum amount of materials, energy already embodied within that. And there's some great examples, particularly in the UK now, and in Canada actually, where they've got existing buildings where actually reuse just the structure. So you kind of strip away the facade, strip away all the services, are reusing the foundations, generally the structural walls, beams, columns. You might be expanding and adding onto that a little bit, but reusing that kind of core structure is preserving you a whole lot of embodied energy and carbon from that displacing of new materials, but it's also saving kind of program time. Yep. So much faster build time, which means your users getting on site quicker, which is saving costs kind of in program, and that added benefit of the person that's kind of wanting to lease that space or whatever is getting in, so you're getting income from the building much faster. So those kind of program benefits, I think, have hugely driven some of those decisions, because actually you can save, if you could save a year of your time, for example, or 6 months of time on site, that's a huge saving.
Definitely. Some of the critics listening might now, if you're looking at operational energy and including in that, a lot of people would say that the existing buildings, are less energy efficient. So over its lifetime, you're going to have more emissions and that side of things. So you're better off knocking it down and then building a new one. Is there a way of getting the best of both worlds? Absolutely.
So I think if you're looking at reusing the existing structure, you're looking at deep retrofit inherently with that. And the example where I'm saying if you're reusing the structure, actually you're completely rebuilding your building facade anyway. and your building facade and your services are actually going to be your drivers generally for your operational carbon side or operational energy side. Even if you're keeping a lot of facade materials, there's some great examples now where you can externally insulate, internally insulate, cavity wall insulate, depending on what you're dealing with, and really improve those kind of benefits. And because of the huge embodied impacts of these buildings, the couple of studies that have looked at this, you pretty much always get a whole life carbon benefit from retaining the existing structure and retrofitting. There's not as much work as I'd like to see there, and it's something as a research group I'm trying to kind of find more ways to look at to demonstrate actually that case across the board and kind of the key things you need to be thinking through.
Yeah, something really interesting that's happening in Australia. I'm not sure you're aware of this project, but there's a 10-storey cross-laminated timber building going on top of an existing 6-storey concrete building. I mean, that's
amazing.
That's a whole another option. Just because I think when structural engineers are designing with concrete, we're designing for the 28-day strength, and then you also get that additional strength if you test the columns. It's most likely that they're going to actually be much stronger. So I think with this extra capacity, they were able to put 10 stories on top of an existing, which you wouldn't be able to do with concrete. So that's, again, a whole new solution we haven't really even touched on.
Yeah, I mean, that's an amazing solution of being able to say, actually, we've got so much over-designed capacity within this building.
Yes.
I think in the UK, I've seen examples where they've gone a couple of stories up, but I've never seen 10 stories up, which is very cool. And I definitely have some students at the moment who are trying to look at comparing sort of adaptability in structures against completely optimized structures and what that does to your embodied carbon. So building in that extra capacity to columns and saying, if I'm enabling future expansion of a couple of floors, what does that do in terms of material mass to my columns compared to a completely optimized design?
That's a really interesting topic. So what? Because I guess on one hand you're putting in extra material to allow for that adaptability, but the adaptability may or may not happen in future. So it's there's a bit of speculation involved with this. So can you comment a bit on what the best solution might be around that?
I think it massively depends kind of where your building is and what you think the future potential of that building is. An optimized structure is giving you a reduced embodied carbon. It depends kind of what your base case and where you start from a little bit. So a lot of the existing projects that you look at will end up being slightly over-designed inherently anyway. So if we were designing more optimally in the first place, I think you'd see a very big difference between a building designed for adaptability and a building that's been completely optimized. But actually, when you say our kind of current base case, the uplift from the studies we've looked at so far of designing for adaptability is maybe giving you 5% more material.
Okay.
In some cases, it was giving you barely any extra material. It depends kind of what adaptability strategies you're looking at. So designing for a higher floor load, for example, so that if you've got an office building, actually if I'm increasing my kind of live load, my variable load, to something like 5 kilonewtons per meter squared, which is going to give me slightly more different types of use that I could use it in the future. So it means I can use it as more of a kind of, braining gear, some more mixed use type uses or gallery type spaces. So it just gives you a few more options. That you weren't actually seeing a huge amount of increase purely because of the amount we kind of over design inherently anyway, compared to the base case.
And just on that, do you think sometimes I look at the design loads, say 3, 4, and 5 kPa loads for office buildings, and for those who aren't engineers, 3 kPa is 300 kilograms per meters squared, and or 500 kilograms per meter squared. It just seems way over the top. Do you think what do you think there, or do you think it's necessary to be this conservative?
I think there's a really difficult balance because the being conservative does give us that kind of unintended future flexibility, which can be pretty useful. And when you look at it, even in how efficiently we don't design that efficiently to that load in the first place. So there's kind of a couple of different steps I think you go through if you're going to try and optimize the structure, because you've got the first, am I even designing straight to code? So there was a study from some colleagues at Cambridge where they looked at this, and they were looking purely at multi-story steel structures. And they found that generally, compared to Eurocodes, which is our kind of structural codes in Europe, that structures had about 50% more steel in than needed to meet the Eurocodes.
Oh wow,
so you've got
that's
a massive
lot.
uplift. So this was it. It was about 20 case studies they looked at. So we're not talking a massive case. 50%.
50%. That's a bit of it is quite terrifying. That's I guess just structural engineers, and if you're a structural engineer, sometimes what they would say in defence of them, they'd say they have to whip up the design so quickly.
Yep,
and in
absolutely.
that case, and if engineering firms will be undercutting each other, trying to put in the cheapest fee, but in doing that, the client will never realise they're paying pretty much twice as much in material fees compared to the most optimised design.
Yeah, and you get this really challenging balance, I think, that you can absolutely see why structural engineers are doing it. There's time savings massively, and everyone is being pushed in the construction sector to deliver things as cheaply as possible, as fast as possible.
Yeah.
And I think this is places where computer software can actually really come into its own, because you can optimize using the software, and actually that's much, much quicker than an engineer having to physically, design everything themselves.
Of course.
And I think bringing that in and kind of harnessing that, yes, there's always going to be a balance between constructability on site. So I'd say you're probably going to get sensibly that down to maybe at least a third. Maybe, you may well be able to get it to kind of actually you're only 10% over what we need, purely in terms of actually for some of these projects I looked at, and some of the steel fabricators I've spoken to in the course of kind of trying to understand this a bit more. Actually, some of it comes down to connection detail and fire design, because actually for some of them, for the much smaller slender beams particularly, or beams and columns, the amount of fire protection that they had to increase actually massively increases. So for them, that becomes much kind of more challenging, and actually would then start to increase costs. So there's this really difficult balance, I think, of practicalities, optimization. And in terms of embodied carbon, I've tried to have a look and I can't find anything. And it's something kind of on my list of things to try and look at properly at some point, is what the embodied carbon of kind of intumescent paint is, or different fire protection strategies, because I don't know where that balance then starts to fall in terms of how well we optimize versus how much fire protection we're adding. And there's a lot of things to try and balance in. So you can absolutely see why you're getting these increases.
I could imagine a builder, if you looked at a drawing and every single beam was designed to the exact same size, and he's going to deal with 100 different size beams or something like that. But it sounds like if, as computers, as you said, start doing more and more of the heavy lifting from the design side and maybe from the BIM side, and hopefully be able to help builders as well, we might be able to get that down to, as you said, closer to, as low as possible, really.
Absolutely. And I think once we design like that, then you can start to question, are these design loads even reasonable? And that's kind of your next step to try and push more efficiency. Yeah,
fantastic. So we've touched a little bit on technology. So as we get toward the end, is there any technologies that you think are exciting in your field?
I guess kind of fringe of my field would probably be around automation and kind of how we bring in AI technologies to either optimize design, or got one project at the moment where we're trying to use machine learning techniques to automatically recognize materials, so that you could start to catalog the materials in a building or materials in a city is kind of my ideal end game, so that we can automatically say this city, so Sheffield,
so
is
how does the AI
this many bricks, and
gotcha.
It harnesses that kind of really labor intensive survey that you'd have to do otherwise.
Does that take photos and it recognizes from an image what materials, or is?
Yeah, exactly. So it's visual recognition algorithms basically that are running, and they give you kind of a certain certainty of, this is 97% chance that this is a brick.
Fantastic.
And I think as we develop that through So part of what we're trying to work on at the moment is, well, you need to automatically recognise something's a window first, and then you can kind of take the window out and say, okay, well, we've got this kind of surface area of windows. So I think that kind of automation of things that traditionally would just be so labour intensive to do is technology which absolutely I think could kind of change how we design and how we approach things. And we're trying to work on developing a digital twin for Sheffield in the long term, so that you've got this kind of replica online of the city, so that, you know, if someone says, oh, actually, I'm thinking about demolishing this building, I'd like them to be able to know at the press of a button pretty much, this is the material stock of my building. You know, what are the options in terms of reusing that building through life or reusing the individual components, so that it's just all a lot easier for people to make those decisions.
Definitely. It's super exciting. Well, coming toward the end now, so if people want to find out more about yourself, Danielle, or your work and your awesome research, where should they go?
So the best bet is probably going to be the University of Sheffield's website. I'm in the Civil and Structural Engineering department, their website, and then my staff page on there, because that has kind of most of the links to kind of my live current projects or my papers and that kind of thing, or my LinkedIn profile is probably the other place.
Hey guys, Adam here. Just before you go, just one quick request. If you're enjoying the show, please leave a review. It helps our rating and ranking on iTunes, so more people can hear from the people who are making our cities better places for our future.